Okay, guys. So in this lecture, you are going to learn in-text and exercise questions. Of course, not exercise. We are going to see in-text question answers from chapter 13 science, that is magnetic effects of electric current, and questions from 224, 228, 229 and 230 pages. Well, coming to the first question in 224 in-text questions, we have a question. Why does a compass needle get deflected when brought near a bar magnet? Whenever they ask this question, you need to analyze that we have one bar magnet and we have one compass needle. Bar magnet has magnetic property. Compass needle has magnetic property. Whenever a material has magnetic property, or if it is a magnet, definitely there will be magnetic field. So while coming to bar magnet, of course, this is north and south. It will have some magnetic field around it. You know how to draw those magnetic fields. And while coming to this bar magnet and while coming to this compass needle, of course, this also will have magnetic field around it, same as bar magnet, same shape you can find it. Now, if both magnets are brought near to each other, if you move this and if you move this, what will happen? There will be one bar magnet and there will be one compass, magnetic compass. Both will have magnetic fields and these magnetic fields will intersect. So magnetic compass needle and bar magnet both have magnetic field. When they brought near to each other, these magnetic fields interact with each other. So if they interact, what will happen? There will be deflection in needle. So here the word deflection. Whenever you have the word deflection, you can think of two things. First one is attraction. Second one is repulsion. Attraction, repulsion. Attraction refers to deflection. Repulsion also refers to deflection. That is a concept you need to understand from that question. Well, coming to page number 228, first question. Draw magnetic field lines around bar magnet. First, you need to draw one rectangle representing a bar magnet and poles your wish, guys. If you want, you can represent south pole this side and north pole this side, or you can represent, you can take bar magnet, you can represent north this side and south that side. There is no any compulsory thing for you to represent left hand side one pole and right hand side one pole. No need of that. But after representing south pole and north pole, magnetic lines are important. So you see, we know magnetic lines always, it will travel from north pole to south pole, it flows from north pole to south pole. So from north, magnetic field line will emerge and it will travel towards south. Arrow marks are important. So this directed diagram you can find in your textbook. So middle line, that should be straight, and that direction, it should enter towards south and that should travel towards north, and from north it will come out. So these are the directions. Next, important question. List the properties of magnetic lines of forces. Okay. Now there are few properties. First property, outside the magnet, the magnetic field lines are directed from north of the magnet towards south pole. So if you observe this diagram, you will come to understand. Whenever you see a magnet from north pole, consider we have a magnet here. Consider this is north pole. From north pole, this magnetic line or magnetic field line will emerge, will start, and it will travel towards south pole and it will enter here. So direction should be like this. So from this we can say outside, magnetic field lines are from north pole to south pole. However, inside a magnet, the field lines are directed from south pole to north pole. So these 2 points are so important. Inside, it will from south to north. Thus, magnetic field lines form a closed loop. So important thing. It is a closed loop. So if you remove this magnet and if you observe, it will be like this, isn't it? This is outside, north to south. This is inside, south to north here, like this. Second point, the magnetic field line at any point points in the direction of magnetic field at the point. Simply to say, consider we have a magnetic field line which is flowing like this, and consider this is the direction. Now, if you place any magnetic compass on the line like that, now this compass also will show the same direction like this. So that is the meaning of that point. Next, the relative strength of magnetic fields is given by degree of closeness. What is meant by degree of closeness and strength? You see, there are two magnetic lines which are like this, and here we have two magnetic field lines which are like this. You see, in this first case, distance between two magnetic field lines is less, and here distance between two magnetic field lines is more. If distance is less, its strength will be more. If distance is more between two magnetic field lines, its strength will be comparatively less. So that is the meaning. The relative strength of magnetic field lines is given by degree of closeness. Degree of closeness means it may be distance of closeness or that value of closeness, unit of closeness, etc. The magnetic field is strong in the region where field lines are crowded. So this magnetic field will be strong whenever lines are crowded. That's what we have discussed in last lecture. And if you see here, this is the point where all lines are very close to each other. So at poles, strength will be high, isn't it? Next, no two magnetic field lines can never intersect with each other. If you have one magnetic field line which is passing like this, and consider there is another magnetic field line which is passing like this, no two magnetic field lines intersect, so it will pass like that and it may pass like this. That is the concept you need to understand from that one. Next, why don't two magnetic lines of forces intersect with each other? So here we have discussed, if you have a magnetic field line, it will not intersect. Why? Because you see, consider we have one magnetic field line which is flowing like this. We have another field line which is flowing like this. Now consider if it is flowing like this and it is moving like this. This is the point of intersection, isn't it? Now, what I told here, this example, if you remember, on magnetic field line, if you place compass needle, it will show one direction, right? And you see, this is the point where here you see no two field lines are found to cross each other. Why? Because if they did it, it would mean that at the point of intersection, this is point of intersection. At the point of intersection, the compass needle would point towards two directions. Means if you place compass needle here, in which direction it should show? It should show this direction or this direction. So it will not, it cannot vibrate, right? And at the same time, that magnetic compass cannot show two directions at the same time. It may show either east or west or south or north, something. Only one direction at one instant. It cannot show multiple directions at one instant, and which is not possible. Right? It cannot show it. It will get confused. So there will be no intersection of two magnetic field lines. From this, you need to understand that. And while writing this answer, you have to mark this point as important. It would mean that at the point of intersection, the compass needle would point towards two directions, which is not possible. This point is important. Next, we have page number 229, one in-text question. Consider a circular loop of wire. Okay, there is a wire with circular loop, it seems, lying in the plane of table. So this is table which is lying on it. Let the current pass through the loop clockwise. Clockwise means this is the direction. Apply the right hand rule to find out the direction of magnetic field inside and outside the loop. Okay, we have a loop which is lying on plane of table. We have kept it on the table. Now, the magnetic field lines have been shown in figure given below. You can see the magnetic field lines. As per the right hand rule, we find that inside the loop, the magnetic field lines are directed perpendicular to the plane. What is meant by perpendicular to the plane of paper? This is middle point of the loop, isn't it? Which will be perpendicular. So if this is the plane of the bench, magnetic field line will be perpendicular, because in last lecture we have discussed exactly in the middle of the loop, magnetic field line will be straight, isn't it? Here you can observe. This will be straight. If this is the plane of paper or bench, this line is paper or bench, and this should be the magnetic field line, isn't it? So this magnetic field line will be perpendicular to the bench, that is in the middle. Next, outside the loop magnetic field are directed through the paper. Now let us try to apply right hand rule. If you observe this right hand rule, okay, first what they told, current is passing in clockwise direction. Clockwise direction means here you can find from here current is passing. Current is passing from here, so it should move like this. You can understand the diagram, I guess, and it will come out here. So this should be positive, this should be negative. Now if you apply right hand thumb rule, direction of current is this, and magnetic field should be like this. So, and again if you observe, current is flowing out in this direction, and magnetic field line which will be like this inside. So while coming to magnetic field line which is in the middle, in which direction should be there? Like this, downwards. So all these you need to analyze, and while writing answer, these points should be present. So first one, we find that inside loop, the magnetic field lines are directed perpendicular to the plane of paper in the inward direction. So perpendicular to the paper in the inward direction means this should be inward like this. Outside the loop, so outside the loop means loop which is present on the table, Magnetic field lines are directed out of the plane of the paper. So you see it is coming out, right? Which is coming out. Here also which is coming out. So those 2 points are so important. You need to analyze this question with the help of diagram. If possible, try to draw diagram and explain this. So in middle line which is perpendicular, which will be inward direction, while coming to outside, the loop magnetic field lines are directed out of the paper. Just simple. Place one circular loop on the bench and try to analyze it. Second, the magnetic field in the given region is uniform. They are saying, they are giving one statement. Draw a diagram to represent it. So whenever you see magnetic field in a given region is uniform, means magnetic field lines should be uniform. If magnetic field is uniform, magnetic field lines will be uniform. So uniform means it should be parallel line, simple. So you can draw like this, or if you want you can draw like this also, correct. Or if you want you can draw like this also, that is correct. Fine, whatever it may be the direction, but all lines should be parallel to each other. You can draw downwards also, that should be parallel to each other. That is so important. Next, choose the correct option. The magnetic field inside a long straight solenoid carrying current. Okay, this is solenoid. In this solenoid, exactly inside, exactly in the middle. How about the magnetic field? So already we have compared that solenoid with the bar magnet. So if you see bar magnet, magnetic field will be outside, will be curved, but while coming to inside, what we have discussed, that should be straight line, isn't it? Straight line from this point to this point, definitely it will be straight. Not only inside, outside also, middle point it will be straight. So 0, no, that is not the correct answer. Decreased as we move towards the end. Decreased as we move towards the end means, so it should decrease like this, or increase as we move towards the end, that should increase. Magnetic field line should increase, it seems. No, both are not happening. Is the same at all points. Here you take, it is straight. Here you take, it is straight. And if you place magnetic compass here, if you place magnetic compass here, it will show same direction. It will, if you keep it here, it will show same direction. If you keep magnetic compass here, same. Wherever the place in the middle line, if you place, magnetic compass will show straight line, isn't it? But if you keep here, it may show in this direction. If you keep, it may show in this direction. If you place it here, it may show in this direction. If you place it here, it may show in this direction. So that magnetic field will be same at all points in the middle of the solenoid or bar magnet. So these are the in-text questions from those page numbers. This question might be somewhat tricky. So you can analyze this one. Consider this is plane of paper and you are placing circular loop on the paper, guys. Circular loop on the paper. Now, if current is passing clockwise, clockwise means from this side current should enter, from this side current should leave. Enter means it will be flowing like this, isn't it? Like this it will flow. Now, according to right hand thumb rule, if current is in this direction, you need to close your fingers. So how you will close? Like this you will close, isn't it? All 4 fingers will be closed like this. So magnetic field will be, which will be coming outside the paper, outside the plane. So will be circular loop, and inside that will be directed towards center, that should be in the downward direction, and outside upward direction, middle downward direction. Simple answer. So by this we have completed in-text questions from these page numbers, and in our next lecture we are going to learn about force acting on current carrying conductor which is placed in magnetic field. So here we are going to learn one important topic, that is Fleming's left hand rule. You are familiar with right hand rule. Now we are going to see Fleming's left hand rule.